Welcome back to this lecture video. Today we will be seeing one of the most important topic in computer science, that is the analysis of algorithm efficiency. However, whether you are preparing for university exams or jobs interviews, understanding this unit will give you a solid foundation how we evaluate and compare algorithms. Okay, here the basic topic covered is the analysis framework, asymptotic notation and their properties, mathematical analysis of recursive and non-recursive algorithms, measuring the input size and unit for measuring runtime, and order of growth. And the last is different types of case efficiencies, that is best, worst and average case. Okay, let's begin with the analysis of framework. Here the topic we are going to see is how we measure an algorithm's time efficiency and space efficiency. Time efficiency is about how fast it runs, and space efficiency refers to how much extra memory it uses. To do this efficiently, we consider the size of input. For example, when performing matrix multiplication, the size of the matrix, say n cross n, becomes our input size, denoted as n. Similarly, in a spell checking algorithm, the number of characters or words becomes the input size. In some case, like binary representation, the input size may be in terms of bits, represented as b is equal to, that we can see here. See, b is equal to log base 2 n plus 1. Okay, next we will be seeing the units for measuring runtime. You might think of measuring time in seconds or milliseconds, but this isn't an reliable way because the time taken depends on the system, your processor, your compiler, and even your programming language. So instead, we use basic operation counts. For example, in sorting, the most frequent operation is the key comparison. So we count how many comparisons are needed based on the input size n. This gives us a much more accurate and machine independent way to analyze an algorithm. Okay. Next is order of growth. Okay. Next is order of growth, which is a powerful way of predicting how our algorithm behaves as the input size increases. For example, if one algorithm takes n square operations and another takes n log n, the second is more efficient for large values of n. This helps us choose the right algorithm for big data. This idea leads us to symptotic notations like big O, theta, and omega, which we will cover in another lecture. Okay, we can see. This is the chart for big O complexity, you can see here. Okay, next we will see worst case, best case, and average case. Different types of efficiency are there. First one is worst case. Efficiency is the maximum time an algorithm can take for an input of size n. Example, searching an element at last index of an element, represented as worst case of n is equal to n. Worst case. Best case, see, best case is the minimum time, like finding the element at the first index, represented as best of n is equal to 1. Average case lies somewhere in between depending on the distribution of inputs. Here we calculate the expected number of steps. All three are important while designing and selecting algorithm for different application. Last, we will be seeing about the amortized efficiency. A more advanced concept is this topic. This is useful when an algorithm performs inconsistently across various operations. For example, in dynamic array like array list or vector, inserting an element usually takes order of one time. But occasionally, when the array size resizes, it takes order of n times. Over many operations, we average out the cost. So, amortized analysis is especially helpful when successive operator or related or independent common in data structures like stack, queue, and hash table. Okay. This is for the today's section of fundamentals of analyzing algorithm efficiency. We discussed how to measure input size, execution time, growth order, and types of efficiency. Thank you.